Hi guys, a very good evening everyone. Once again, welcome all of you to your favorite learning platform for GATE engineering services and all technical examinations for EC, EE and IN aspirants. And yes guys, I Rakesh Talreja welcome all of you once again. And as you know, we have been having IIT Roorkee PYQ sessions. Okay. Yes, IIT Roorkee conducted the examination in 2017 and 2009. Okay, and we have been specifically looking into the previous year questions only of subject to subject, like control system. We had two different sessions. Signal and system also I have planned two sessions. Unfortunately, part one was done, but unfortunately part two, which was there last week, due to technical issue, I had to stop it. Okay, there's a very little I could do, and I have to stop it. But now, yes, again, I told you. Okay, whether a technical issue came, that is not in our control. Sometimes it happens, but now today I'm coming up with the part two once again to cover up all the questions. And yes, let me just see if the audio video. Unfortunately, yeah, audio video all looks good. Okay, let's get started. Let's get moving ahead. You can also update all your friends that the session is now live, and so that we start up the discussions. Okay, let's start up the discussions, everybody. Okay, dear. Okay, this is a regular introduction about me. Starting with the first question straight away. Okay, starting with the first question straight away. The ROC of the Z transform of the discrete time sequence. ROC for the Z transform of the discrete time sequence. Xn equal to 1 by 3 power n un minus 1 by 2 power n u minus n minus 1. Okay, 1 by 3 power n un minus of 1 by 2 power n u minus n minus 1 will be how much? Okay, what will be the ROC for the Z transform of the discrete time sequence? Okay, so Z transform, one very regular expected question is about ROC. So whenever we have a power n un, okay, the ROC for a power n un, okay, is given by mod z greater than mod a. Okay, mod z greater than 1 by 3, straightforward. Okay, for a power n u minus n minus 1, for a power n u minus n minus 1, it is given by mod z less than mod a, that is mod z less than the half. Okay, here the value of a is half. Okay, so what is the common ROC? It should be greater than 1 by 3 but less than half. That means between 1 by 3 to half. Between the 1 by 3 to half. Option number A, straightforward question it is. Okay, option number A, straightforward question it is. Next question. Next question. The Z transform of a signal is given to you 4z power minus 3 plus 3z inverse plus 2 minus 6z square plus 2z cube. Okay, it is applied to a system with the transfer function. Okay, hz is equal to 3z inverse minus 2. Let the output be yn. Which of the following is true? Okay, which of the following is true? Okay, there are four options. Now, the Z transform of a signal is given and the transfer function, the system information as well as the input information is completely in the Z domain. Okay, now, see, if I talk about time domain information we have to convolute. Yn is xn convolution, hn is the impulse response. But in the Z domain, convolution in time corresponds to multiplication of Z domain, Z transform. So xz into hz. Okay, now the xz and hz are given to me. What is the value of xz? Okay, that is 4z power minus 3 plus, okay, 3z inverse plus 2 minus of 6z square plus 2z cube. This is to be whole multiplied by hz, which is 3z inverse minus 2. See, no need to do the complete multiplication. No need to do the complete multiplication. What I can do here is, see, I can say that z power minus 3, z power minus 1. The lowest term will be 4 3 z 12, z power minus 4. Okay. Okay, then there will be possibly some z power minus 3, z power minus 2 terms with some coefficient which I am not calculating right now. Up to what term? Up to what term? Okay, there may be this term plus or minus a z power minus 3 plus or minus b z power minus 2 up to what is the highest power of z. So see, z cube into z inverse will be still z square, z cube into 2. Okay, so let's multiply. 2 2s are 4, minus sign is there. So minus 4 z cube. This is the highest term. This is the yz. Now dear, we know that this yz, the z transform formula is actually summation of yn z power minus n. Summation of yn z power minus n. So if this is z power minus 4, this is the value of y4. Okay, similarly, there will be some value of y3, which I have not written here. And similarly, this is z power plus 3. Now, z power plus 3 will come if n is minus 3. Okay, so this means it is y of minus 3. Okay, so yn, the output exists for n equal to minus 3 up to n equal to 4. That is what clearly I can say that. Okay. For minus 3 up to the time 4. Okay, now on the basis of this, let us see the options now. Okay, yn is non-causal with finite support. Yes, it is non-causal. Is it causal? Causal means yn should be 0 on the left side. Okay, yn should only start from n equal to 0 or after it. Okay, so yn is definitely non-causal. Okay, yn is definitely non-causal. Okay, and with finite support, with total finite length. Okay, option number A. Option number A. Option number A itself is correct. Here it is. Option number A is correct. 3 is wrong. Mod n less than 3. No, n equal to minus 4. Mod n can be greater than n equal to 4 is also there. Okay, so option number A is what is matching up. Okay, and then if one option matched MCQ, no need to think about the D, because here you have to convert Z transform into, you know, sort of DTFT e power j omega, and then you have to check, but no, not required. That is not required, correct? Next question. Any doubt you can let me know. A system with the transfer function Hz has the impulse response Hn, which is defined as H2 equal to 1, H3 equal to minus 1 and Hk equal to 0. Consider the following statement. Hz is a low pass filter. Okay, filtering based question, very important. Okay, and Hz is a FIR filter. Is it FIR? Okay, like previous question also we talked about that finite support there case. Now see here. FIR. Okay, the system has a transfer function Hz and the impulse response Hn. See the impulse response Hn, which is defined as H2 is 1, H3 is minus 1. Okay, only two non-zero values are given and Hk is 0 otherwise. Okay, so what is that value? It starts from n equal to 2. It starts from n equal to 2. The value is 1 and then next value is minus 1. This is n equal to 2, but you have to at least specify where the origin is or what the value at the origin is. You have to specify that. So what is the value at the origin here? Okay, so this is n equal to 2, na? So back n equal to 1 and n equal to 0. Okay, dear, I can put it like this. This is n equal to 0, then 1, then 2 and 3. Okay, so only two non-zero value, others are 0, but I have to include the arrow. That is the origin. That is n equal to 0. Okay, so what is the length of Hn? It is finite. Okay, what is the length of Hn? It is finite. So does it represent FIR? Yes. Okay. It is finite in length, and whenever any impulse response in finite length, okay, that is a FIR filter, finite impulse response filter. That is finite impulse response system, no doubt here. Okay, not a doubt here. Okay, now whether it is a low pass or high pass. Now see, the idea of low pass, high pass, you can calculate either from DTFT or from Z transform. See, how do you calculate, dear? How do you calculate? First of all, Hn, let me retake it here. 0, 0, 1 and minus 1. Correct? Yeah, but this is the origin. So what is the Z transform corresponding to it? What is the Z transform corresponding to it? So Z transform starts with 0, okay, and then 0 and then 1, okay, into Z power minus 2, because again I'll use the same formula, summation Hn Z power minus n. Okay, so this is 1, and what is the value of n? This is origin n 0, so 1, 2, 3. This is n equal to 2, so Z power minus 2. Next value minus 1 multiplied by Z power minus n equal to 3. Okay, that means what is the Z transform of the system, transfer function of the system? This is Z power minus 2 and minus Z power minus 3. Okay, we have the Hz now. Now, whether it is low pass or not, how will you comment whether it is low pass or not? Very important question. It's a GATE 9 EC 2 mark question. This 2017 also you will find filtering question. Okay, so come up here. Just a second. Let me choose that background. Okay, what is that? Let me choose that background. What is that? Okay, so now when I talk about low frequency, okay, low frequency refers to omega equal to 0. Now see, generally Z is R e power j omega in the Z transform, but when we go to the frequency domain, when we convert it purely to the frequency domain, that means when you convert to DTFT, Okay, the DTFT is obtained by taking R equal to 1, R which is mod Z equal to 1. Okay, DTFT is the Z transform evaluated on the unit circle, right? And in that case, Z is e power j omega. And if you take 0 frequency, Z equal to e power 0 will be 1. So if you solve using DTFT, you have to put omega 0. If you solve using Z transform, you have to put Z1. Okay, what about high frequency? What about high frequency? High frequency omega equal to pi. Any DTFT is periodic with period 2 pi and one time period information is considered minus pi to pi. The highest positive frequency is the pi. Okay, highest frequency is the pi. And what about Z? Okay, Z. Now e power j pi is minus 1. E power j pi, when you expand cos pi minus j sin pi. Okay, now sometimes only low and high frequency required, sometimes some intermediate frequency. Frequency will also be required to comment on the nature, and you can take any intermediate frequency, but for simplicity let me take the midpoint pi by 2. Okay, so Z is e power j omega, e power j pi by 2, cos pi by 2 plus j sin pi by 2. It will be equal to j. It will be equal to j. So Z will be j. Okay, so now dear, what is the hz? Okay, let's solve this question. Yeah, let's solve this question. What is the hz obtained? Z power minus 2 minus Z power minus 3, or 1 upon Z square minus 1 upon Z cube. Let me start with low frequency. For low frequency, I will put Z1. Okay, what is the value of H1? Okay, will be 1 upon 1 minus 1 upon 1 and 0. This is very clear. It is not a low pass filter. If it was a low pass filter, it should pass the low frequencies, na? It should pass the low frequencies with higher gain. And it is just rejecting the low frequency. It is definitely not a low pass. Okay, is it low pass? It is definitely not low pass, but it is FIR. As far as this question is concerned, okay, so I can say that only statement S2 is true. Option is A. Clear? Option is A. It is not low pass 100%. But okay, let's go in depth and check if it is not low pass, whether it is high pass or band pass, what type of filter it is. Okay, this question is solved, but let's continue. Okay, now let's take the high frequency. Z equal to minus 1. Okay, what is h of minus 1? Place the value here. 1 upon minus 1 square will be 1. Minus 1 cube will be minus 1. So this is 1 and minus 1 is plus 1 plus 1, 2. Yes, it is passing the high frequency. To understand the pattern more, if I take the intermediate frequency where Z is equal to J, okay, what is h of J? What is the h of J? Is 1 upon J square. J is minus 1 and J cube is minus J actually. Okay, so this is 1 upon minus 1 and minus minus plus. Again, 1 upon j is minus j. So I can write it as minus j only. Since it is complex, let me calculate the magnitude, the gain. Okay, what is the gain? Mod of hj under root of x square plus y square under root of 1 square plus 1 square root 2. Okay, so what exactly is happening? Roughly, if I draw the picture, na? Roughly, if I just draw the picture. Okay, let me draw it in the mod of h omega domain. Suppose if I take h omega, okay, what is the characteristic? At the 0 frequency, the gain of the system is 0. It is not low pass. But as the frequency increases, the gain is increasing and the maximum magnitude seen is equal to 2. Maximum magnitude seen is equal to 2. Approximately, let me draw a curve here where the gain, this is equal to 2 at what frequency? At the frequency pi. And at the intermediate frequency pi by 2, at that intermediate frequency pi by 2, the gain which was seen was root 2, 1.4 approximately. And because the impulse response given is real, 1 and minus 1, only real values are there. Okay, so the magnitude spectrum is even symmetric. Okay, so if you want to extend this up to the minus pi, this is the answer. Okay, this is what is the filter characteristics. Clearly, it is a high pass. When you go towards high frequency, okay, they are being passed with higher gain. It is not ideal high pass filter, okay, but it is a sort of high pass filter. It is a sort of high pass filter. It is a sort of high pass filter, correct? So whether this question asks whether it is low pass, that is wrong. So option number A. But what type of filter if they ask? This is high pass filter. What type of filter if they ask? This is high pass filter. Okay. Have a look into the next question. The pole 0 plots gate 17 EE1 mark. Okay, and these filter based questions are important for EC, EE, and for all of them it is important. Okay, hi RRK. Okay, the pole zero plots of three discrete time systems PQR on the Z plane are shown below. Okay, which of the following is true about the frequency selectivity of these systems? Frequency, whether all of them are high pass, all of them are band pass, or you have four options given. Okay, PQR, pole zero plots are given. Now see, P, there are two poles at origin. Okay, and then this is unit circle. Now dear, if this is unit circle, see this is origin. Unit circle means radius 1. So this should be 1 and this should be the minus 1. Okay, so first of all, let me write down for P, what should be the transfer function? Okay, there are two zeros at 1 and minus 1. Okay, there are two zeros at 1 and minus 1. Okay, so the numerator should be Z plus 1, Z minus 1, and denominator pole is Z square. And there may be some constant gain K. Okay, this is what P system is. Okay, this is H1Z. So I can call it as K, A plus B, A minus B, A square minus B square, the Z square minus 1 upon Z square. Okay, this is H1Z. What about the second system? Let's come to next. Okay, it has poles, it has zeros at plus and minus 1. Okay, so J plus Z plus 1, Z minus 1 again. Okay, this is 1, this is minus 1. But poles, okay, at y-axis, that is J 0.5 minus J 0.5, imaginary axis. So what is the denominator I should write? Z plus J 0.5, Z minus J 0.5. And when I simplify this, numerator again A square minus B square, Z square minus 1. Denominator also I apply A square minus B square, but J square is minus 1. Minus minus plus, and 0.5 square, 0.25. Okay, this is the second one. Okay, third one. Okay, third one. So you see this. Zeros again and 1 and minus 1, and poles is at J and minus J. Unit circle pa ye, this is imaginary axis, so J and minus J. For the system R, I will write down the transfer function as again Z plus 1, Z minus 1, and for denominator Z plus J, Z minus J. Z plus J, Z minus J. Correct. This is further now equal to K Z square minus 1 upon Z square plus 1. A square minus B square, but J square is minus 1, correct? This is what it is. This is what it is. Okay, so now if I identify what is what? Okay, if I identify what is the H1Z? K Z square minus 1 by Z square. Okay, low frequency, H of 1. Low frequency, I put Z equal to 1. H of 1, Z equal to 1, 1 minus 1, 0. It is not low pass. Okay, intermediate frequency and high frequency. What is high frequency? Z equal to minus 1. Okay, Z equal to minus 1. Okay, but again, minus 1 square is same 1. 1 minus 1, 0. So it is not high pass also. It is not passing low frequency. It is not passing high frequency. So definitely it must be passing some frequencies, some band of frequencies. Okay, for that let me try intermediate frequency, and for that I put Z equal to J. J square is minus 1. Okay, minus 1 upon again J square, which is minus 1. So overall it is 2K. Overall it is 2K. So at intermediate frequency you have some gain. At intermediate frequency you have some gain. And approximately if I draw the plot now, approximately if I draw its plot here, okay, there is no low frequency gain, there is no high frequency gain. Okay, so definitely gain must be increasing. It reaches some value 2K and then decreases. Okay, this is pi by 2. So it is the sort of filter where I can say maybe some band of frequency is being passed by the system. This is a type of band pass. First one is band pass. Okay, first one is band pass. Okay, second one, what is the H2Z obtained? Okay, numerator being the same, K Z square minus 1 upon Z square plus 0.25. Okay, so again low frequency H of 1, 0. High frequency H of minus 1, again 0 because minus 1 square is 1. Okay, and you know this result will be same for the third system also. Because numerator is the same, zeros are same. Okay, denominator is Z square plus 1. So H of 1, okay, again 1 minus 1, 0. H of minus 1, again 1 minus 1, 0. What you have to calculate is the H of J. Okay, what I should figure out is the H of J. H of J, J square minus 1. Okay, so minus 1 upon minus 1 plus 0.25. Okay, so this is again some gain in between 2 upon, how much it is? 0.75. 2 upon 0.75, correct, na? So around twice 2.67k, some 2.67k, and here, okay, it is k minus 1 divided by minus 1 plus 1, okay, infinity, okay, and very large gain, okay, very large gain. Okay, so all of them are basically band pass. Okay, there is no gain at low and high frequency. Okay, all of them are typically band pass. Okay, so option number B. All of them are band pass. Okay, so I'm telling you, these questions are important, filtering based question, and that is why I'm solving in detail, showing you the real calculations like previous question also. Okay, this was gate 17, previous one was gate 9. This is gate 17 EC 1 mark question. HN is given now in the form of impulses. Okay, HN is given now in the form of impulses. Again, let's do this quickly. So let's find out the transfer function HZ. See, 5 del n. What is the Z transform of impulse? You know that 1. Okay, then 7 delta n minus 1. Okay, Z power minus 1. Okay, time shifting. If del n has the Z transform 1, okay, del n minus 1 will have the Z transform 1 into Z inverse. That means Z inverse. Z power minus n naught is multiplied time shift property. Next is 7 del n minus 3, so Z power minus 3. Next is 5 del n minus 4, so Z power minus 4. Okay, so collecting the terms together, dear, I have h of Z is equal to 5 minus 7 Z inverse, so that is minus 7 by Z. Okay, plus 7 Z power minus 3, so 7 by Z cube, and last is minus 5 upon Z power 5. And let me do the calculation. Low frequency H1 calculation. So 5 minus 7 plus 7 minus 5, 0. It is not low pass, 100%. All the terms cancelled. Okay, let me first take the high frequency calculation, that is h of minus 1. Okay, so 5 is constant. 7 upon minus 1 will become plus 7. Minus 1 cube will be minus only. So 7 upon minus 1 minus 7. And minus 1 power 4 will be plus 1. So here it is minus 5. 5 and minus 5 cancel. 7 minus 7 cancel. It is not low high pass also. It must be band pass. Okay, it must be band pass. Without any doubt, you can mark the option as C. Without any doubt, you can mark the option as C. But let me still calculate for you. So now h of j, you see 5. Okay, minus 7 by j. 1 upon j is minus j. So I will write it as plus 7j. 7 upon j cube. J cube is minus j. But 1 upon j minus j. So overall, this will also be plus j. Correct now? Plus j. And minus j power 4 is 1. So this is minus 5. 5 and 5 cancel. But 7j plus 7j is 14j. Yes. And if you calculate the magnitude, gain of the system, 14, definitely. Okay, in between, for some set of frequency, it has a higher gain. Okay, but the low and high frequencies are blocked. Band pass. Already I have shown you the answer, band pass. J is 1. Okay, the correct answer is option number C. The very correct answer is option number C only. Okay. Okay, now next question, gate 17 double E 2 mark, very good question. Okay, this one is a very good question asked in double E. Okay, so for 2 marks, consider a causal and stable LTI system with the rational transfer function Hz, whose corresponding impulse response begins at n equal to 0. And furthermore, h1 equal to 5 by 4. h1 is equal to 5 by 4. The poles of Hz are pk equal to 1 by root 2 exponential of this. The zeros of Hz are all at z equal to 0. Let Gn equal to j power n Hn. What is the value of G8? Before coming to Gn, you have to talk about Hn. And what is the information given? What is the information given about Hn or Hz? It is causal and stable. Okay, whose corresponding impulse response begins at n equal to 0. So Hn starts from origin. Okay, corresponding impulse response, okay, begins at n equal to 0. Hn starts from n equal to 0. That means I can say that h of 0 will be non-zero. There will be some value. Furthermore, h1 is given to you, the capital H1 transfer function. The poles of Hz are given to you. Now, dear, the poles, okay, are given by pk equal to 1 by root 2 e raised to the power j 2k minus 1 pi by 4, odd multiples of pi by 4. Okay, for k equal to 1, 2, 3, 4. So if I put down k equal to 1, 2, 3, 4, I will be getting 1 by root 2 e raised to the power j, k equal to 1. Okay, so first you get pi by 4, then 1 by root 2 e raised to the power j 3 pi by 4, odd multiples of pi by 4 you will get 1 by root 2 e power j 5 pi by 4 and 1 by root 2 e raised to the power j 7 pi by 4. Now dear, a small simplification. Okay, when you want to talk about, see, the transfer function h of z can be written as k into some numerator upon denominator function of z. Okay, k nz upon dz, something like that we can write this. Okay, we can write it something like that, correct? Fine, we can write it something like this. Okay, now where what is dz? The denominator, I can write that separately. The denominator, I can write it separately. How I can write down the denominator? Okay, there are 4 poles, 1, 2, 3, 4. We can convert this into the Cartesian form. Okay, z minus p1, z minus p2, z minus p3, z minus p4. Okay. So the roots are known, I know the factors then, and I multiply, I get the denominator. On solving, what do you get? Okay, we can save some time here. Okay, on solving, what do you get? On solving, you are going to get it as z power 4 plus 1 by 4. You can try this. You will get it as z power 4 plus 1 by 4. Now, zeros, okay, of hz are all at z equal to 0. The zeros of hz are all at z equal to 0. And one more important point is h of 0 is not equal to 0. H of 0 is not equal to 0. H of 0 is not equal to 0. H of 0 also represents initial value. Okay, now what is the initial value of a signal? As per the initial value, okay, it is given by limit of z tending to infinity hz. Okay, now this is non-zero. Now, dear, a simple mathematic rule. This is a very good question. Some good mathematics will keep coming here. K nz upon dz. Okay, so whenever limit z tending to infinity for numerator by denominator expression is non-zero, okay, that is only possible. See, there are 3 cases. Whenever degree of numerator more, you are solving z tending to infinity, and whenever degree of numerator more, answer will be infinity. Whenever degree of denominator is more, answer will be 0. Whenever both the degree are 0, then only you have a non-zero finite answer. Okay, so that means degree of numerator must be equal to degree of denominator. That means number of zeros, numerator will give you zeros, na? And denominator will give you poles. So number of zeros is equal to number of poles. And how many poles are there? 4. How many poles are there? 4. So zeros will also be 4. But whatever are the zeros are all at z equal to 0. Are all at z equal to 0. So what are the zeros? Zeros are all at z equal to 0. But how many they didn't say? I have given you that idea. So there will be 4 zeros at origin. Okay. So now what will be the numerator function? Numerator function can be simply z power 4. The 0 is z equal to 0 coming 4 times, so z power 4. Okay, so what is the hz now? Hz is k, okay, numerator z power 4 upon denominator z power 4 plus 1 by 4. Okay, where given to you h of 1 is how much? H of 1 is 5 by 4. Okay, h of 1. So when you put z equal to 1, k into 1 upon 1 plus 1 by 4, and this is equal to 5 by 4. Simplifying this will also become 5 by 4, correct? Into right side. So 5 by 4 into 5 by 4, 25 by 16. K is 25 by 16. Okay. Now you see h of z. Okay, it is k z power. I'll divide by z power 4 throughout. So 1 upon 1 plus 1 by 4 z power minus 4. Okay, yeah, you can say I multiplied by z power minus 4, and I'm writing now this denominator, I'll shift it to the numerator. It becomes 1 plus 1 by 4 z power minus 4 whole inverse. Apply 1 plus x whole inverse. Apply the 1 plus x whole inverse, and it is written as 1 minus of x plus x square minus x cube, etc, etc, etc. Now, dear, whatever is the term that you see here, this is z power minus 8. Okay, whatever is the term you see here, what is multiplied by z power minus 8? That should be h of 8. That pattern I have shown you in the previous question also. Okay, h of 8 z power minus 8. So what is h of 8? What is multiplied? 1 by 16 into k. K into 1 by 16. K is actually written outside common, and k is 25 by 16. So 25 by 16 further multiplied by 1 by 16. So 25 is divided by 256. That is the value of H8. That is the value of H8. 25 upon 256. Okay. Now the question is find the G8. Okay. G8. Gn is J power n Hn. Okay. Next, what is given to you? Gn is J power n H of n. Okay. So what should be G of 8? Okay. That should be J power 8 H of 8. Okay, J power 8 is 1, so that is simply H of 8, and H of 8 I just calculated. 25 is divided by 256. Numerical answer type question it is. Okay, let me convert the value. Okay, approximately 0.097. 0.0976 or 0.097 or 098 I can write down. Anyways, it's okay. Okay, so 0.097. Very good. One of the very, very good finest question of Z transform. And that too coming in the double E branch. Okay. Even better than the EC question. Okay. So that's what signals. It's not like many people believe that signals for double E will come simple. For EC it will be good level. No, it can be anything. In EC also we find several good questions. But this is in the GATE PYQ history. Not only 2017 or 2009. Not only IIT Roorkee. But to be honest, this is one of the finest question. Okay. Detailed question on Z transform. Okay, dear. Okay, fine. Chalo. If this is fine, let's move ahead to the next question. Where I went? Acha, oh, sorry, the slide went back. This question we were into, one of the very, very good questions. Let me mark it again. Okay, and let's move ahead to the next question then. Here it is. A continuous time signal xt equal to 4 cos 200 pi t plus 8 cos 400 pi t. Okay, where t is in second is the input to a linear time invariant LTI filter with the impulse response. Okay, 2 sin 300 pi t upon pi t for t not equal to 0, for t equal to 0, 600. Okay, let yt be the output of this filter. Let yt be the output of the filter. What is the maximum value of modulus of yt? Now see, this filtering based question. We come back to Fourier transform, continuous time Fourier transform question. It is the input to LTI filter with the input. Yeah, correct. Okay, so have a look into it. Dear, see, impulse response 300 pi t upon pi t. Matlab somehow we can represent this in the sampling or the sinc function. Sampling or the sinc function. See, what you can write this as. This is 300 pi t, this is only pi t. So multiply and divide by 300. 2 into 300 sin 300 pi t is divided by 300 pi t, and then this is equal to how much? 600. Okay, sin theta by theta is sampling function. So sampling 300 pi t. 600 sampling 300 pi t, correct? 600 sampling 300 pi t. Fine. Chalo. Okay. And anyways, dear, one more thing. What is the value of sampling 0? See, I have used a sampling function here. Let me specify to you. When I use a sampling function, sampling x, okay, I mean sin x by x. Whenever you can also express in the sinc function of, sinc function is actually taken as sin pi x upon pi x. If you express in sinc function, so let me also tell you that sinc theta is equal to sampling pi theta. Okay, fine. So now, what is the value of sampling 0? Sin 0 by 0. Sin 0, limit x tending to 0, sin x upon x is 1. Okay, so even if I put down t equal to 0, sampling 0 is anyways 1. So 600 into 1 will be 600. So even if this second condition is not given, it is understood. It is understood. Okay, so what is my impulse response? Let me specify here separately. What is my impulse response? It is 600 sampling function. What is that sampling value? 300 pi t. Okay, sampling function represents, if you have studied in detail, you must know that the sampling function represents a low pass filter, ideal low pass filter. See, why? Because whenever you have the sampling AT, Fourier transform pair, sampling AT has the Fourier transform in the rect function. Sampling AT has the Fourier transform, okay, pi by a rect of omega by 2a. It is given by the pi by a rect of omega by 2a. So dear, what is the frequency? Now this is the impulse response, correct? What is the frequency response of the system? H of omega. Can you write this, please? I've given you the formula also. What is the h omega of the system? Okay, so that will be pi by a. A is 300. Okay, 2a will become 600 pi, correct? 2a will become the 600 pi. Okay, so what is that h of omega? Okay, it is pi cancel 2 rect of omega by 600 pi. What is the h of omega? Is 2 rect of omega by 600 pi. And when I sketch this, okay, when I sketch this h of omega, okay, modulus of h omega will be h omega only. It is a purely real function anyways. Versus omega. Okay, modulus of h omega versus omega. So what do you have is a rectangular function, omega by 600 pi. Omega by, what is this denominator in the rectangular function? That represents the total width of the rectangular function, total duration. Total width is 600 pi. So minus 300 to 300. Let's say this is minus 300 pi up to 300 pi. It is a constant value. Rectangular means flat curve, and that flat gain and that constant gain is known as 2. Okay, and this is clearly an ideal low pass characteristics. Okay, any frequency up to the 300 pi is passed. Okay, with equal gain, that is 2, and any frequency beyond 300 pi is rejected. Okay, and this 300 pi is then known as the cutoff frequency of the filter, and this is clearly an ideal low pass filter having gain of how much? Having the gain of 2 and the cutoff frequency equal to 300 pi. Okay, if any frequency you pass through a system, if you pass a signal having frequency less than 300 pi, it will be passed with gain 2. And if you pass any frequency greater than 300 pi, it is rejected, blocked. Okay, ideal low pass filter it is. Okay, ideal low pass filter. Now, what is the input given to me? 4 cos 200 pi t, 8 cos 400 pi t. Let me write down this input. What is the input? Xt is 4 cos 200 pi t plus 8 cos 400 pi t, correct? Let me check it out. Yeah, this is the input given to me, correct? Now look into the frequency component. Okay, this is the sinusoid having how much frequency? Cos omega t. You can directly compare omega 200 pi. Okay, sinusoidal hai, so you don't have to convert into frequency domain. You can directly say the frequency component of it 200 pi, and it is below omega c. And if it is below omega c, it will be passed. Okay, and the other sinusoid has the frequency 400 pi, which is greater than the cutoff frequency of the filter, and hence it will not be passed. It will be rejected by the system, and hence I can write down the output now directly. I can write down the output directly. Okay, the component which is passed will be passed with gain 2. Will be passed with gain 2. So if the input is 4 cos 200 pi t, output should be twice of that. Okay, another one is rejected. Okay, so that will not appear in the output. I will make it 0. Okay, and hence the final output is 8 cos 200 pi t. They can ask you the output expression also. If this is the input, find the output expression. But here they have converted into a numerical answer type question. Okay, and what is the maximum value of modulus of yt? Okay, so so 8 into cos, maximum value 8. It will be oscillating between minus 8 to 8. Modulus I need to consider means positive value. Answer is 8. Answer is 8. Numerical answer type question. I'll mark it as 8. Okay, the final answer as 8. Good question. In 17, you will find, questions around filter, whether it is the discrete filters or continuous filter. Okay, discrete filter, simple technique. You can put Z equal to 1, minus 1 and J. Low frequency, high frequency, intermediate frequency concept I told you. If it is continuous time filter, it will be some analysis based. Fourier transform formula and some analysis. They will be more thoughtful and more detailed question. Okay, let's take another one. Let's keep rolling ahead. Let's keep rolling ahead here. Gate 17, EE 2 marks. Again, a very good question. I can tell 2017 especially signals, EC, EE both branches, very good level. Very good level. Okay, some questions were straight, but some questions are very good. Okay, let the signal xt equal to, summation minus 1 power k delta t minus k by 2000 be passed through an ideal low pass filter with the frequency response h omega. Okay, so now see, in this question, actually our main point will be understanding the input xt because the frequency response is given. Last question I find out the frequency response. Here it is directly given, and again it is the ideal low pass filter, very clear in front of us. This is ideal low pass filter. Okay, with the cutoff frequency. Okay. Okay, with the gain equal to 1. Okay, so gain will be 1 only, and with the cutoff frequency of 5000 pi. Any frequency up to 5000 pi passed, otherwise reject. Okay, ideal low pass filter is given to you. Okay, you have to understand input. Okay, now input image I have brought to you directly so that we save time here. Okay, input, because this question is again little detailed question. Input summation -1 power k delta k t minus k by 2000. First understand this equation. So summation minus infinity to infinity. Okay, you can take minus infinity to infinity. I have taken some term starting from 0. So if you take k 0, -1 power 0 will be 1. Only delta t will be there. If you take k 1, okay, this is corresponding to k0. Now if I take k1, so -1 power 1 negative. So alternate plus minus, -1 power odd negative, -1 power even positive. So this is minus delta t minus 1 by 2000. Correct. Now if I take k equal to 2 dear. Okay, so again -1 power 2 plus 1 I am telling now, alternate plus minus delta t minus 2 by 2000, and etc 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 plus minus will keep rolling. Okay, so have a look into it. Okay, have a look into it. Let me explain you this picture. Okay, let's say this is t equal to 0, where I get the delta t, positive impulse. Okay, then delta t minus 1 by 2000, I have a value of time. Okay, delta t minus t naught means right shifted impulse. Where it is right shifted? 1 upon 2000, and having how much of area? -1. Then delta t minus 2 by 2000. Okay, this is 2 by 2000. Okay, where again I have a positive impulse. Similarly, next 3 upon 2000, again negative impulse, etc. Left side, this will be -1 by 2000. Okay, -2 by 2000, and etc. It's a periodic. It is very clearly a periodic signal. This is xt. Okay, this is xt, which is very, very clearly a periodic signal. Okay, because there's a repetition. Positive and negative impulse is one period, then positive, negative, that cycles repeat. That cycle is repeating. Clear? Okay, what is the time period? Now, if it is a periodic signal, it should have a time period, fundamental time period, minimum value of time after which repetition occurs. What is that minimum value of time? What is that minimum value of time? This much, capital T. Okay, sorry, I have taken from 0 here. Correct only. Sorry, let me mark it from here. Positive to positive. Okay, this is my time period. Positive impulse to the next positive impulse, the minimum time after which repetition occurs, and that is coming out to be 2 upon here. This is 0, this is 2 upon 2000. So time period is 2 upon 2000, or I can call it as 1 upon 1000. Okay, so frequency, if you want in hertz, it will be 1000, or if you want in omega, okay, that is 2 pi f, so that will be 2000 pi. 2000 pi, that will be the omega. Okay, this is the information about the signal. Okay, this is the information about the signal. Now, dear, for any periodic signal, okay, some Fourier series funda, Fourier series and Fourier transform combined funda will be used here. Okay, if it is a periodic signal, okay. Achha, before that, let's calculate the Fourier series coefficient. Because it is periodic signal, na? What are the Fourier series coefficient? Ck. Okay, so actual formula for Ck is 1 upon t integral over one time period xt e power minus jk omega naught t dt. Okay, 1 upon t integral over one time period xt e power minus jk omega naught t dt, or simple shortcut Ck is 1 upon t xp k omega naught. Okay, where what is xp? xp omega is the Fourier transform of one time period xpt. Suppose out of the periodic signal you extract one time period. Learn some techniques and tricks here. For this periodic signal, you just extract one time period. Within one time period, what do you have? Dear, in the one time period, you have two impulses, one positive and one negative impulse. Let me call it as xpt, one time period information of the signal. One time period information of the signal. That has one positive impulse, del t. Okay, what is this? I will write down here only del t, and then that negative impulse. Okay, minus del t minus 1 upon 2000. Correct. And then after that repetition, I separate out only one time period. After that it is repetition. So dear, what is the xpt here? Del of t minus del of t minus 1 by 2000. So what is the xp omega? Fourier transform. See, because Fourier transform of signals, Fourier transform of important signals is usually known to aspirants. It is usually known to students. So that is why it is easy to find it using the Fourier transform. Or actually you can use the Fourier series coefficient formula also. Okay, so impulse Fourier transform 1. Again impulse Fourier transform 1, but time shifting property. Time shifting brings the exponential phase term in the frequency domain, e power minus j omega t naught, that is 1 by 2000. This is xp omega. Okay, now what is ck? Now what is ck? 1 upon t xp k omega naught. Okay, what is time period? 2000. Sorry, time period is 1 by 1000. So reciprocal of time period will become 1000 into xp k omega naught. Omega naught is 2000 pi. Omega naught of the signal is 2000 pi. Omega naught, fundamental frequency of the signal. Okay, 2000 pi. Okay, so now place down the value. It is 1000. What is xp omega? 1 minus e power minus j omega 1 by 1000. Put omega equal to 2000 pi k. E power minus j in place of omega, I put 2000 pi k into 1 by 2000. Okay, so 2000 cancelled, and your Fourier series coefficients are 1000, 1 minus 2000 cancel, to e power minus j pi k. E power minus j pi k. Now again here, we can write down the value ki whenever k is even, like 0 or 2, k0 e power 0 1, k2 e power j2 pi k. Okay, when you open e power minus j2 pi k from cos 2 pi k minus j sin 2 pi k, you will again get the answer as 1. Okay, for any even value of k, e power minus j pi k will be 1, and 1 minus 1, ck will become 0. And if you have any odd value of k, e power minus j pi, suppose k is 1, so e power minus j pi, write down cos pi minus j sin pi, write down, it will be minus 1. Okay, similarly, it will repeat. Okay, so 1 minus 1, 2, so 1000 into 2. Okay, so ck will exist only for odd value of k, it will not exist for even value of k. Okay, this is about ck. Now, what are all the frequency terms in the signal? Okay, let me open up the Fourier transform and show the result to you. Let me open up the Fourier transform and show the result to you. Ck is equal to 2000 for k equal to odd. Okay, 2000 for k equal to odd, correct? For the k equal to odd, ck. Okay. Hello. Yeah, let's continue. So that's what. Now, once you have the Fourier series coefficient, once you have the frequency information, again, you can see which frequency will be passed, which frequency will be rejected, because it is a low pass filter. Okay, now ck are known to me. Na? What will I do is, ck are known to me. Okay, because ck is known to me, applying the Fourier series here. Okay, or you can go to Fourier transform also. But if I directly apply the Fourier series, in Fourier series, we write down a signal xt as summation of ck e power jk omega naught t. Summation of ck e power jk omega naught t. Okay, for all values of k, minus infinity to infinity. But here only k equal to odd will be taken. Here only k equal to odd will be taken. Okay, so what I will consider is only k equal to odd, because for k even ck is 0. So that particular term will not exist. Okay, so xt, there will be a lot of terms. So if I take k odd, starting with the negative, okay, minus 3, okay, c minus 3, okay, c minus 3, and all the ck are 2000. Don't worry. C minus 3 e power minus j 3 omega naught. Next will be c minus 1, only consider odd, e power minus j omega naught t. C1 e power j omega naught t. C3 e power j 3 omega naught t. Till infinity. Now I'll put down the value of omega naught. There will be so many terms. All this c is 2000. Okay, to 2000. Okay, e power minus j. What is omega naught? Omega naught fundamental frequency as we calculated is 2000 pi. Okay, so e power minus j 3 omega naught 6000 pi. Okay, c minus 1 again 2000. This is e power minus j omega naught 2000 pi t. Next, again 2000 e raised to the power j 2000 pi t. Next, Fourier series coefficient 2000 e power j 3 omega naught 6000 pi t. Now remember dear, okay, what is the cutoff frequency? The cutoff frequency of the ideal low pass filter, as I have shown you in the question, is 5000 pi. The cutoff frequency is 5000 pi. So if I apply that cutoff frequency, okay, because it is 5000 pi, okay, so this is greater than cutoff frequency. The magnitude of frequency is 6000 pi. Okay, this is also greater than omega c. Okay, greater than cutoff frequency, and it is a low pass filter. So this is going to be rejected. This is going to be rejected. This one, 2000 pi, this is less than 5000. Okay, so this is going to be pass. And what is the gain of the filter, as we have seen? 1. Similarly, this is also less than omega c, so pass. Gain 1 means same gain. 2000 into 1, 2000 will appear. So what is the final output then? What is the final output then? What is the final output? Okay, only these two terms will appear. Okay, that is 2000 e raised to the power minus j 2000 pi t, plus next is 2000 e raised to the power plus j 2000 pi t. Use the Fourier series to solve this question. Okay, and then I can take 2000 common. Okay, e power j theta plus e power minus j theta is 2 cos theta. Okay, 2 cos theta, and theta is 2000 pi t. Final answer, okay, 4000 cos of 2000 pi t. 4000 cos of 2000 pi t. Okay. 4000 cos of 2000 pi t. Option is C. Option is C. Correct answer is option number C. Again, good question, conceptual question. You need to know the concepts. You need to have the understanding of the Fourier series and Fourier transform to get hold of this question. Okay, some more Fourier series based question. Actually, I have solved in the previous part also, signals part 1. Okay, some Fourier series question we solved there, and then the time was almost over. So I am now taken some questions in this one, and also I have taken Z-transform questions. Okay, and some more questions to come up. Okay, so you can watch the part 1 also if you have not watched. In the part 1, you have some Fourier series question, convolution question, classification of signal, basic properties of signal system. All those questions are there. Okay. One more question on continuous time filter. Again, gate 17 EC 2 mark. Okay, I'll give you as homework. See, again, sinusoidal input is there. Okay, so you have to understand what type of filter it is. It's not going to be a low pass filter this time. It's not an ideal low pass filter, I should say, like that. Okay, so you have to sketch what type of filter it is. Okay, magnitude and phase both given. Okay, magnitude and phase both given, and then apply. Okay, apply to the given information. This one I'll put it as homework. Okay, this one let me put it as homework. Move to the next one. Okay, if a continuous time signal xt is cos 2 pi t is sampled at 4 hertz, what is the value of the discrete time sequence xn at n equal to 5? Okay, sampling frequency, very fundamental, instrumentation 2017 1 mark question. Okay, sampling frequency is 4 hertz. So what is the sampling time period ts? It is 1 upon fs. So it is 1 upon 4. Okay, or 0.25. Okay, now what is the sampled signal? Okay, when you sample xt, okay, how do you write down the sampled version? We write down the sampled signal as x of nts. We write it as x of nts, that is x of n by 4, and that will become, if xt is cos 220 pi t, x of n by 4 will become, okay, cos 2 pi into n by 4. Okay, you have to just put the t as n by 4, that is nts. Okay, so that becomes cos of pi by 2n. Now, what is the value at n equal to 5? Simple question, na? What is the value of the sequence at n equal to 5? At n equal to 5, it will become cos 5 pi by 2. See, now cos pi by 2 or any odd multiple, cos pi by 2, 5 pi by 2, 3 pi by 2, 7 pi by 2, all of them are 0. Cos 5 pi by 2, 0. Cos 5 pi by 2 is 0. Answer is option number C. So this is a simple. It's 1 mark only anyway. 17 instrumentation 1 mark question. Okay. Answer is 0. Simple one. Okay. Next one. Another one on sampling only. The output of the following system is to be sampled so as to reconstruct it from a sample uniquely. What is the required minimum sampling rate? Dear. Okay, the required minimum sampling rate, also known as the Nyquist rate. Okay, and it is in samples per second, that is in hertz. Okay, that is in the form of hertz. And what is the Nyquist rate? Okay, it is given by 2 omega m. Nyquist rate, okay, that is omega s minimum. It is given as 2 omega naught. Okay, 2 omega m. Omega m is the maximum frequency component of the signal. The maximum frequency component, or sorry, if it is in hertz, okay, I will call the Nyquist rate as fs minimum. That will be equal to twice of fm. Fm, highest frequency component of the signal. Now, we have to calculate the Nyquist rate of yt, and there is some block diagram given. xt is the input, okay, having the Fourier transform x omega, which is first fed to a multiplier. Okay, xt cost. So what is the information here? Now this is a LTI system whose input is xt into cos 1000 pi t. Okay, it's a gate 17 2 mark. Again a good question. Okay, again a good question. Xt into cos. Now whenever any signal is multiplied by cosine, modulation, okay, its spectrum is shifted to higher frequencies. Its spectrum is shifted to higher frequencies. Okay, centered at plus or minus omega naught. Okay, and then it is passed through ht. Okay, which is again, see, sine 1500 pi t upon pi t, sampling function, ideal low pass filter. See, what is the ht? Okay, multiply by 1500 numerator and denominator. 1500, then I will write sine 1500 pi t upon 1500 pi t. That I am writing as sampling 1500 pi t. Okay, so this is going to be an ideal low pass filter. Ideal low pass filter. What will be the h omega? What will be the h omega? As I told you, formula. Okay, as I've told you the formula already. Okay, sampling 80, pi by a. Pi by a. What is a? 1500 pi. Pi by a. Rect of omega by 2a. Okay, so 2a becomes 3000 pi. So pi 1500 getting cancelled, and h of omega is rect of omega upon 3000 pi. Rect of omega upon 3000 pi. It is the omega upon 3000 pi, correct? That is omega upon 3000 pi. Ideal low pass filter. Cutoff frequency will become 3000 pi, 1500 pi. Total width is 3000 pi, na? Correct? Ideal low pass filter, okay, with the cutoff frequency of 1500 pi. Okay, now xt. Now x omega is given to you, dear. Okay, if yt, suppose, no, sorry, that is output yt. Let me call it as some signal xt yt. Let me call it as some intermediate signal wt. Let me call it as wt. Okay, and if the wt is given by how much? Wt is given by, yeah, let me better call it as zt. Okay, ww will confuse with the frequency. This is some signal, suppose z of t. Okay, and z of t is xt cos 1000 pi t. So what is the z of omega? Modulation property. X of, now see, xt multiplied by cos of 1000 pi t. The spectrum will become x of omega plus 1000 pi, shifted to higher frequencies, centered at 1000 pi and minus 1000 pi. So x of omega plus 1000 pi, x of omega minus 1000 pi divided by 2. Okay, what is this? This is known as the modulation property. This is known as the modulation property, dear. Okay. Now x omega is given to me. X omega has been given to me. Not a problem. Okay, it's a triangular signal. Okay. So now you shift it, left shift to 1000 pi, right shift to 1000 pi. And let me draw this information. Now you see. Okay, I'm going to draw z omega. Okay. Now, x of omega minus 1000 pi. Okay, you are going to right shift to 1000 pi. So this minus 1000 pi will come to 0. 1000 will go to 2000. It will start from 0 and it will go up to 2000 pi. And this is the center at 1000 pi. Similarly, when you left shift by 1000 pi, it will go from 0 to minus 2000 pi. This is 0, correct? And the gain here, nothing is given. Okay, so if it is whatever is the gain here, okay, it will be divided by 2. Okay, whatever was the amplitude, suppose I call it as 1, so this will be 1 by 2. Okay, now it is passed. It is passed through the system, which is actually ideal low pass filter. It is passed with ideal low pass filter. Okay, now this is going to be passed through ideal low pass filter having the cutoff frequency 1500 pi and gain 1. Okay, so when you pass it through 1500 cutoff frequency 1500 pi, so any frequency up to 1500 pi will be passed, and any frequency beyond this will be rejected. This will be rejected. Okay, so what will be the highest frequency component? Without sketching the output, the highest frequency component will be up to 1500 pi. Will be up to 1500 pi. If you want, I'll draw it for you. I'll draw it for you. So what is the output Fourier transform? Without drawing, you can conclude the answer. Okay, but if I draw it for you, okay, the output y omega, okay, and that is going to look like something of this kind. This was 1000 pi, and yes, somewhere at this point. Because all frequencies above 1500 pi are not passed, they are rejected. And similarly, it was identical on the left. Okay. So now, dear, what is the highest frequency component of the signal? This becomes FM, the highest frequency component of the signal. The highest frequency component of the signal is 1500 pi. Okay, that is actually in radian per second. Okay, I should actually call it as omega m first. Okay, so what is FM? Okay, it is always omega by 2 pi. Okay, so that is 750 samples per second or hertz. And what is the Nyquist rate then? Okay, that is the minimum sampling rate, Fs minimum, and as I told you, it is given by twice of Fm. So 1500, twice of it will become 1500 hertz or 1500 samples per second. Answer is option number B. Good question again. Good question. 2017 really good signal and system. 2017 good signal and system, I can say. Correct? In the 2017 you can feel the good signal and system. Okay. Let's move ahead to the next question then. Good analysis, waveforms you have to sketch, Fourier transform, multiple properties you have to remember. Okay, 17 EC2 mark. This is more like a regular sampling question. Okay, more like a regular sampling question. Okay, the signal xt is sine 14,000 pi t, where t is in second, is sampled at the rate of 9,000 samples per second. So what is given? See, first of all, okay, xt is sine 14,000 pi t. Okay, so what is the frequency component of the signal? Highest frequency. Sinusoidal has, sinusoidal omega naught has two impulses at omega naught minus omega. Okay, so considering positive side, what is the only frequency signal component? And that will be highest frequency component also. That will be, okay, first, if I write it in the form of omega n, that is 14,000 pi, or if I write it in Fm, divide by 2 pi, so it is 7,000, or I can say 7 kilohertz. It is 7 kilohertz. Okay, and then it is sampled at the rate. Now, what is this sampling frequency is given? Fs is 9,000. Okay, the sample signal is then the input to an ideal low pass filter. Okay, with the HF given to you. Now, see, HF equal to 1 for mod F less than 12. That means F is minus 12 to 12. So, what is the cutoff frequency? No need to sketch it. See, if you sketch it, what they say, the mod of HF, the HF is equal to 1. Okay, for any frequency, okay, less than 12, mod F less than 12, that means F is minus 12 to 12. So this is the cutoff frequency. Cutoff frequency 12 kilohertz. 12 kilohertz. Okay, what is the number of sinusoids in the output and the frequency in the kilohertz? Okay, and the frequency in the kilohertz. Okay. Dear, first of all, recall. Okay, very basic formula. What is the Fourier transform of the sampled signal? Dear, the Fourier transform of the sampled signal, XS omega, is basically given by summation. This is a very basic step in the sampling theorem once you study. Summation of x omega minus k omega s for k minus infinite to infinite. Okay, that means this XS omega, okay, contains several terms running from minus infinity. Okay, if I take k minus 1, you will get x omega plus omega s. okay, then plus of x omega, okay, then k equal to 1, x omega minus omega s till infinity. So there will be x omega, the Fourier transform of the original signal. Okay, then, okay, right shifted by omega s, right, another right shifting by 2 omega s, etc. Left shifting by omega s, left shifting by 2 omega s, etc. On the basis of this, let me plot. Okay, and what is the input given to be? Sinusoid. Okay, now whether it is sine or cos, sine will have a negative impulse, but let me consider sinusoid. Na? Okay, output they don't want the sketch. Output they want only how many frequencies will be available. So let me draw. Okay, for the sinusoid, two impulses. Okay, let me draw for the sinusoid two impulses. For the sinusoid, okay, there will be two impulses, and let me directly plot the results on the frequency f scale, considering frequency directly kilohertz. Okay, and I want to draw the excess. Yeah, forget. I just want to don't mention on the y-axis here. Let me draw. Okay, so sinusoid. Okay, what is the frequency of the sinusoid? 7 kilohertz. So there will be two impulses, 7 and minus 7. There will be two impulses, one at 7 and minus 7. One will be at the 7, one will be at the minus 7. Okay. Okay, one will be at the 7 kilohertz. Okay, one will be at the minus 7. And because it is sine signal, there will be a negative impulse. If it is cos, it is positive impulse. Doesn't matter. Even if you draw both positive, doesn't matter, because the output waveform they are not asking. They are asking how many frequencies will be there. Okay, this is one Fourier transform, x omega ya xf. Then you have to right shift by omega s, 2 omega s, and also left shift. Okay, what is omega s ya fs? Let's do it in the fs scale. So fs is how much? Fs is 9000. That is 9 kilohertz. Fs is 9 kilohertz. So right shifting by 9. Here right shifting by 9 is 9. Minus 7 plus 9. Okay, minus 7 plus 9 will be 2. Okay, will be 2. Okay, 7 plus 9, 16. Okay. Another right shifting. Now these are the two new impulses. Another right shifting. 2 plus 9, 11 will be there. 2 plus 9, 11 will be there. 16 plus 9, 25 will be there. Okay, another 11 plus 9, 20 will be there. And etc. Similarly on the left also. Now left shifting. These were the original impulses. Left shifting by 9. So 7 minus 9. 7 minus 9 minus 2. You will get this symmetry here actually. Okay, and minus 7 minus 9 minus 16. Okay, so left side pure symmetry will be there. If there is 11, there will be minus 11 also. Okay, and Acha, I have drawn all positive. Sorry, if I have started with negative. Sorry, I have started with negative, so I should complete that. Anyways, okay, sorry. But yeah, I hope you got the idea now. Okay, I just have to plot it again. Okay, right shifting by 9. So minus 7 plus 9, minus 2. This one will minus. So 7 plus 9, this will be 16. Yes, dear. As I told you, the power will be back soon. Okay. Yeah. So now this is one shifting. Now another shifting by 9. Okay. So minus 2 plus 9. Sorry, this was plus 2. 2 plus 9, 11. Okay. Let's say this is 11. So we have it 11. 16 plus 9, 25. Okay. 25. Okay. Now again, 11 plus 9, 20. So 20 means negative impulse. 25 plus 9, etc. It will keep going here. Okay, now similarly symmetry will be there. Okay, as I've already shown you, symmetry will be there. Okay, so then sorry, this was my first one, na? Minus 7 and 7. Left shift by 9. Left shift by 9, so 7 minus 9. Okay, this will be at minus 2. Minus 7 minus 9, take it to the minus 16. Okay, now minus 2 minus 9. Okay, that will be minus 11. Okay, minus 16 minus 9. Okay, this will go to minus 25. Okay, and again minus 11 minus 9, this will be at minus 20. This will be at minus 20 and etc, etc, etc. Now, this is going to be passed through ideal low pass filter. This is going to be passed through ideal low pass filter having the cutoff frequency 12. So let me place that ideal low pass filter here. Cutoff frequency 12 kilohertz. Okay, this is the ideal low pass filter having the cutoff frequency of 12 kilohertz. Okay, so when you see the output, okay, how many frequencies will be there? Output will contain how many frequencies? Let me pick up the positive ones. So 2, 7 and 9. 2, 7 and 11. Okay, and how many? Okay, how many? Total 3. Total 3. 2, 7 and 11 and number is 3 of course. Once you know the frequency, then the count is obvious. 2, 7, 11, 3 number of frequency. Option is B. This is more like a regular. Such type of sampling questions are very repeated in exams like GATE. But previous one was good. Previous one was good. Okay, some property knowledge and some depth information is required in the previous one. Correct? All right. That's how it is. Okay, guys. So now important updates for all of you. Okay, Mohan, good to know that you have learned. So guys, if you take the signals part 1 and part 2, if you see the signals part 1 and part 2, I have covered the questions of ECEEIN, 3 branches, okay, for 2017 and 9, 2017, 2009, IIT Roorkee. I have covered the basics of signals, operations on signals, classification of signal, classification of systems as well. There were a lot of questions of classification of system also. Then convolution we have covered, Fourier series we have covered, Fourier transform, continuous time Fourier transform we have covered, Z-transform we have covered, sampling theorem we have covered. Probably Laplace, now I think time is up, only Laplace, but few questions of Laplace and easy. Okay, Laplace you can I think figure out yourself, but very few questions and that too on an easier level only, nothing complicated. Okay, some are very straightforward and some are just basic calculation, nothing different in the Laplace is there actually. Okay, for DFT was not there in 2017. DFT was not there in 2017. Only one question. See, DFT is important for EC. 2009, one question was there. DFT, very simple, very, very simple. 2017, there was no DFT question I found, but that rarely happens. DFT otherwise, see, if I say last 10 years, maybe 2017 is the only year where DFT was not there, but usually it doesn't happen. So EC students, DFT important, not for EE, but EC students, DFT is very important. But there was no question of DFT in 2017. Otherwise, I would have taken that. Okay, so guys, the next GATE regular offline batch for 2025 ECEE, okay, live at our Hyderabad center, okay, starts 11th of August. Okay, the fee 66,000 is currently priced at 56,000. You can take the benefit of it, and also at the same time, okay, there are multiple scholarships like 50% for IIT and NIT students, 50% for OMOL students, 30% for IIIT and state government students. Okay. So, if for any more details, you can contact 95156-94043 or visit our website ominstitute.com. Okay, in case due to any challenge you cannot come to Hyderabad Center for offline batch, okay, and still want the same content by the same faculty team, 100% same faculty team without any deviation, okay, yes, you can also enroll to our online batch if you want to study at your place, at your comfort. Okay, for GATE 25, GATE 26, online live batches for ECEE are available. Okay, the fees for GATE 25, 29,999 is currently priced at 19,999. Okay, and for GATE 26, currently it is 28,999. You can watch these live classes, okay, at our OM Live app or our website, ominstitute.live. That means you can watch it through mobile or as well as browser web, on the laptop, anywhere, at any place you can watch. Okay, same live, because it is live batch, so you can even interact with the faculty and keep asking the doubt. Same set of faculty, same, same level will be covered up. Okay. So again, for more details, you can contact the numbers as I mentioned, 95156-94053. Okay, that's it from my side. I'll sign off right now. Okay. See, Mohan, what you can do is, you can just make a formula chart separately for all transforms like Fourier transform, formula chart and property chart. Okay, for Fourier transform, then for Laplace transform, Z-transforms and DTFT. These are the 4 areas where you can make formula chart, okay, and keep visiting it. And of course, ultimate way to remember them is practice. If you practice, then only they settle. Okay, because questions you are seeing sometimes time shifting property, modulation property, convolution property. Okay, then if you talk about more questions, you expect questions on time derivative property. Okay, and frequency differentiation property. A lot of cases are there. Okay, in some of my previous sessions, you can watch my signals revision course. There you will find the formula directly if you want in some of my signals, and I'll plan here also in my in this Ohm Institute channel also. You'll get signals revision. Okay, when we come more closer to exam, we'll have revisions and formula based session as well. So there you can collect it. By the time you can plan and make a simple table containing list of all important signals. Okay, form Fourier transform of important signals and Fourier transform property. Similarly, do it for other transforms as well. Okay, guys, this is Rakesh Alreja signing off. I'll share you this current this session PDF. I do share my PDF in my Telegram group, but my rule is the PDFs are password protected, because if you watch, you will get the password. Okay, and if you watch, then only you need the PDF. Otherwise, it is not useful for you, and I don't want to spread it for those who are just not studying. Okay, so if you are studying, then only you need the notes, then only you deserve the notes. So what to take for today? For today, simple one, sampling. The last question was on sampling. I randomly think about the password. The last question was on sampling, and I keep the password as sampling. You can note down this password. PDF will be shared in my Telegram group. Okay, if you are already connected, okay. Otherwise, you can search by my name, or you can also search directly by this identity. This is my Telegram ID. Okay, sampling, everything in small, sampling. You can find using it. This PDF will be password protected. You can put this password and open the PDF. Okay, that's it. Bye bye. Thank you. Good night. Stay safe and do take care of yourself.